Good morning. Let's continue with the discussion on the stacking effect. So, the idea was this. Suppose you had a single NMOS transistor with the gate grounded. Of course, the body is also grounded here. Maybe I should write that explicitly. And suppose you had two transistors in series like this. This is also VDD. Both these gates are grounded. Both bodies are also grounded now, right? And the assumption was, okay, this is of width W. Each of these transistors has a width of W, right? So now the question is, how different is the leakage current through these two stacks, right? So we made some assumptions. If we assumed 1, ideality factor n equal to 1, right? Then body effect gamma equal to 0. Then Dibble eta equal to 0, right? We made these assumptions and maybe one more assumption, but we'll come to that when needed, right? And we found out that if you make these assumptions, then this intermediate node Vx basically goes and settles at phi t ln 2, correct? And therefore, if you look at the leakage current through this stack, I think I had the current through the bottom transistor, right, is I naught into W e power what? Yeah, VGS is 0, right? So it is minus VT by phi t into 1 minus e power minus VDS, that is Vx by phi t, right? And if you substitute Vx equal to ln 2 into this equation here, what do you get? You get this to be I naught into W by 2 into e power minus Vt by phi t. This is what we got. And if you look at the leakage current through this transistor, I leak, it is basically I naught into W, right, e power minus Vt by phi t, right? Assuming that VDD is much larger than phi t, you can neglect that term, right? So the assumption was also large VDD, and typically if you have to quantify this large, VDD is greater than 3 times phi t. That's when that 1 minus e power, it will become 1 minus e power minus 3, and that is negligible, is approximately 1. Okay. So the first conclusion that we got from this was, if you don't have any of these short channel effects, then the two transistor stack simply reduces to a single transistor with half the width, right? So if you look at this, if I now make this W by 2, right, then this equation would become W by 2 and the two currents will be equal. So putting two transistors in series is like adding two resistances. So if a width W gives you a resistance R, then the net resistance in series will be 2R, which is equivalent to a width of W by 2, right? So that's the basic idea here. But so therefore this is really not the stacking effect. In a sense, there's no big advantage here, right? Because I'm just getting the effective width reducing because of this thing. So if I have to make a comparison, I have to really make it with these two transistors, width of W by 2 single transistor stack, width of W, 2 transistor stack, right? Then I have to see if I get a current saving. It's only then that I actually can use this stacking effect very effectively. So now let's look at what happens when we introduce these short channel effects. Okay, so this is in reality, right? So I have a single transistor VDD and okay, ground 0. So do you remember what I called N1 and what I called N2 in last class? Can you tell me? Top is N1. Okay, just to keep the notation consistent. N1, N2. Okay, this body is grounded. This body is grounded. This is grounded. Okay. So now let's just calculate various parameters and we'll see what the effect of these short channel effects are, right? Which means basically gamma is not equal to 0, eta is not equal to 0. That ideality factor, it doesn't matter too much, okay? So we can also put that in. N is equal to 1.5 now, right? But VDD is still large. VDD is greater than 350. That still holds, okay? So the VDS of this transistor here, right? Let me call this N0 of N0 is what? VDD, right? VDD. Now what is VSB? 0, right? So therefore, what will happen to this VT of N0? It will be VT0, but there will be this Dibble effect, right? There's going to, so it will basically be VTH0 minus eta times VDD. Okay. Now we will write down the corresponding equations for these two transistor stack as well. Okay. N1, N2, VDS, VSB, and then VTH. Okay. What is VDS for? So this is, by the way, Vx. So for N2, what is VDS? Vx, right? And Vx is where? 5T ln 2. You just saw it, right? Somewhere very close to ground, couple of millivolts actually, right? It's not even, if 5T is 26 millivolt, ln 2 is less than 1. So it's even less than 26 millivolts. So it's nearly ground. Okay. Now what about VSB? 0. VTH for this bottom transistor. So it will be VTH naught minus eta times Vx. Now VDS for N1. VDD minus Vx. Right? VSB is what? No, Vx. Now VTH therefore should be VTH naught plus gamma times root of Vx plus psi s, right? Minus root of mod psi s, right? And minus eta times. Yeah. So now what is happening is the top transistor, right? So this Vx is going to go up a little bit, by the way, okay? It won't be exactly 5T ln 2. It will be, in reality, it will go settle at some different value. You can actually calculate it correctly by substituting this equation in there. You take VTH to be, VTH naught plus gamma times root of that minus eta times VDS. If you apply that equation and solve it, you can find out exactly. I'll point you to a paper where this discussion has happened. You can read it for your own understanding. Okay. We will just look at the intuition here now. So now what is happening is the top transistor is seeing a much lesser VTH than N0. So the transistor N1 is seeing a much lesser VTH than N0. Okay, and when I say much lesser, remember, because the leakage is exponentially dependent on VTH, even that small dibble effect can make a big difference to this leakage current, right? And obviously amongst N2 and N1, right, the guy who can permit lesser leakage is going to sort of determine the leakage eventually, because it's a series path, right? So therefore, in reality, this I stack 2, right, will be much lesser than I stack 1. Primarily coming from dibble, right, 1. Now what about the body effect? If you take N1 transistor, the VSB is obviously greater than 0, because Vx is settling at some value between 0 and VDD. So VSB is non-zero, and therefore VTH goes up also because of the body effect, right? So basically VTH of N1 increases because of 1 dibble. 2 increases compared to N0. VTH of N0 is minus eta times VDD. Here it is minus eta VDD is there, but there is plus eta times Vx. So the VTH increases compared to N0 transistor, and 2 because of body effect, right? Of course, this is the one that's going to dominate. Okay. So any questions here? You can refer that paper and go through that whole derivation, right? It's a very interesting derivation that happens. The key point I want to convey here is, if you just take a long channel device without all these short channel effects, then you will not get that much of a saving. It comes because of all these short channel effects. That's the key point that I want to convey here. Okay. And of course, leakage itself became a problem only because of short channel effects. So, you have to use it only here. You don't have to use it in a long channel device. Okay. Now how do I use this technique? Okay. So let us look at this. Just consider a simple inverter chain circuit, because we have not done other gates till now. I will not go into that. Let's assume that this is my circuit. Okay. My input A, output Y. Okay. Now if the input is 0 here, this will be 1, 0 and so on. And then you're going to have a leakage current, right? So let's assume both NMOS and PMOS leakage are equal, right? So if there are N gates, the leakage will be N into I of either the NMOS or PMOS. It doesn't matter. Let's assume both are the same, right? N gates are now leaking in parallel. And let's say this is very high. Now, how do I reduce the leakage? Okay. So the thing is, one thing to do is to take this inverter and convert it to a 2-stack inverter like this. A, Y. So now what happens, even if it is 0, then I have a 2-stack NMOS transistor stack, right? And therefore the leakage will be exponentially lesser per gate. If it is 1, then the PMOS will be leaking, and I'll have a 2-stack PMOS this thing, right? Of course, the issue here is later we will see that the delay will go up significantly, because now I have to discharge through 2 transistors in series. Effectively, it's like R plus R, the resistance is 2R, rather than discharging through just R. Delay is going to go up significantly. So therefore, this cannot be done at every single gate level. Okay. So for that reason, what is done is people adopt this technique of a sleep transistor. Okay, sleep transistor idea is like this. I want to pull out the ground nodes of all these inverters, right? That is basically this node. Okay, normally I would connect it to ground. I'm now going to disconnect it from ground, and what I will do is I will add one transistor like this. Okay, maybe I should draw in red so that I can maintain the color consistency. That ground node I have disconnected and put an NMOS transistor in series between that ground. So this I am going to now call as virtual ground. Okay, and this is my actual ground. So between the virtual ground and the actual ground, I have added an NMOS transistor, and I will control this by the signal called sleep. Okay, or I will call it sleep bar. So what will happen when sleep equals 0? Yeah? Yes, the NMOS transistor, right? And this transistor, I'm going to call it the sleep transistor. The sleep transistor will turn on and connect the virtual ground to ground, right? Only thing is, it has to be really large, because now what's going to happen is all these inverters, at least every alternate inverter, because the signals get inverted every stage, will discharge simultaneously into this. There can be a parallel current, right? All these currents, and these I am talking about on currents. Okay, so I have two modes of working. One is the sleep state, other is the actual state, right? In mission mode. In mission mode, I want this virtual ground to be as close to ground as possible. For that reason, my sleep transistor has to be very, very, very large. This is basically called mission mode, right? Virtual ground is nearly ground. If W of sleep is very, very large, let's say large. Okay. Now, if sleep equal to 1, this is basically sleep mode. Right? What will happen when sleep equal to 1? The NMOS transistor is, sleep transistor is off. Now what happens to the stack of every single inverter now? Every single inverter on this, right, is now going to see 2 stacked transistors from the output to the ground on the NMOS side only, not on the PMOS side, right? You're following me? So if I take this particular inverter, this guy is actually just our regular inverter, PMOS, NMOS, and then it's coming to the virtual ground. A, Y, this is my virtual ground. So if I take this path, it is from Y. Let's assume that this A was 0. Then the NMOS transistor is supposed to leak. But the NMOS transistor is now seeing its source connected to virtual ground, which means that there is a path that goes through this sleep transistor. And therefore, every single gate in that circuit will now see at least 2 transistors on its stack, which means that the leakage is going to drop exponentially, right? I can do the same thing on top as well, because for the PMOS I need another stack, right? So therefore, you take the the power connection of these things, right? Call it the virtual VDD ground, the VDD connection, and connect this to through a the other way, PMOS transistor to VDD. This is virtual VDD. This also will be connect sleep bar. Is it sleep or sleep bar? Because when sleep is 0, I want it to be in mission mode. Correct. It should be connected to sleep, right? This transistor also has to be large. Okay. So this stacking effect. So the idea is very simple. You make your logic circuit as you want. You don't worry about leakage at that point, right? Make everything you can put NAND gates, OR gates, everything, right? Then you get a circuit where you're connected between VDD and ground. Finally, you just remove this VDD connection, make it a virtual VDD, ground, make it a virtual ground, and connect these sleep transistors in between the virtual grounds and actual ground. Okay, or virtual VDD and actual VDD connection. Right? Then you are able to control this very, very effectively. So this is a very powerful technique to control the leakage in the sleep state. So when your mobile is not being used, for example, then the operating system can actually figure this out and put it into the sleep mode. Why? Because when sleep equal to 0, I want it to be in mission mode. That means the PMOS should turn on. Correct? When sleep equal to 1, it should be off. Yeah. Why? Should be large. Okay. So now let us look at what is going to happen in my mission mode. Okay. I'm going to connect all these things through. So in mission mode, this is connected to 1, right? So let's assume that the input made a transition. This will now make a transition like this, then like this, right? So what will happen is, from every alternate inverter, you're going to have a discharge current, right? And this is on current, mind you. This is not off current, right? In the transient phase, this is an on current, and all that current has to flow through this. Now, if this transistor has a very small width, then the only way this transistor can accommodate a very large current is to increase VDS. Correct? If VDS increases, my ground node is actually going to bounce. The virtual ground node, which should be very close to ground, is actually going up. Now that will ruin your circuit. So the only way you can maintain that high current through this and also keep the virtual ground node very close to actual ground is to have a very, very large width. Right?